Hello, everyone. Thank you for all the brave people that are still there at 5 p.m. last talk. So I make the assumption that you're there because you really want to listen to this talk. So I try to give some, let's say, crunchy details. And if you don't find it detailed enough, like come and we can speak afterward. So I work at Grafana Labs, a company about dashboard. So I listened yesterday to the amazing keynote from Christian, and he had like really strong opinions about dashboards, but I don't take it personally because at Grafana Labs, we are a dashboard engine company. So basically we're building an engine to build nice dashboards so that people can build useful dashboards. Meaning like for me, security-wise, dashboards where instead of data, maybe you have some signal, some useful stuff. Again, we'll try to give those details. Grafana Lab is all about transparency. So basically, we're going to talk about mistakes we make. We use Go, and yeah, when you make mistakes, you can have like security issues and all that. And the goal today is to share. Again, about the keynote yesterday, we discussed about misaligned incentives and all that, and bug bounty hunters, like pen test and all that. And we tend, especially in those conferences, to glorify hacks. But what interests me more as an engineer is how can we make it hard to happen? How can we make things secure enough and all that? How do we make the life of bug bounty hunters harder? So that's kind of my daily job. AppSec engineer, used to be a backend developer 10, 15 years ago. And I worked at GitLab also as AppSec. And basically at Grafana Labs, I try to make sure that the software we are writing is secure enough, meaning that we don't aim for it to be perfect. We want it to be somehow like safe enough, at least better than most of the competition and all that, so that if bad things happen, we don't feel ashamed. We feel we've made a job that's good enough. So we will see that like just a few words about Go and why, if you hear about it, it's nicely connoted, and anytime you talk to people or not, like you hear the message that, yeah, if you do something in Go, it sounds it's going to be secure. But you can still like make mistakes because there are a few things that are confusing, and many vulnerabilities occur when there is confusion. So what we're going to do, we are going to analyze in detail two CVEs. First, a high, where we had a past traversal because of a confusing method. We'll see what we've done to try to make sure we have properly fixed, because we didn't want to play whack-a-mole. We wanted to make sure that once we patch it, we are not like pinged again at the middle of the night to fix it again, because the fix is not like, let's say, wide enough regarding like what it's trying to protect from. So we'll see how we've decided to use Go Fuzzing to try to build confidence on our fix. And after that, we look at something that's worse, critical 9.8 score, where we have suffered from a rest condition and things that where you don't think they could be happening in Go, but they can happen. And there we'll see how we use load testing to exploit the issue we had, and also to make sure, or at least to gain reasonable confidence that our fix was, again, fixing enough the issue so that once we deploy it, like bug bounty hunters don't look at it and just trying to find a similar bypass, and then we really look stupid. And then we'll finish here with something more surprise for the end, just to keep you awake and so that people don't leave before the end. So if you look to go.dev, they say, yeah, well, with Go, you can build simple, secure, and scalable systems. It's kind of really a strong assertion, like simple, secure, scalable. it looks like, yeah, it's a perfect language. Like you should speak it and you can do whatever. You're in good hands. And yeah, if you look at more in the details, yeah, first it's memory safe. So no buffer overflows issue and all that. It's statically typed, which means like it's going to be hard to get like things like remote code execution that we just saw before, with this blockchain stuff and all that. And they also have a nice Golang security checker. So by default, you get a linter that gives you rather good warnings on when you are doing dangerous things, and all that. Yet, as I said in intro, we had several vulnerabilities. We look at 2 because of what I call unexpected behavior, but it's not unexpected behavior like C, where depending on the compiler and the CPU, it doesn't compute the same thing. Here in fact, it's deterministic. And if you look at details in the doc, it tells you exactly what it's going to do. And it's deterministic, whether it's like running on x86, on ARM64 and all that, Mac, Windows or whatever. But it's surprising to the developer. So it's doing something that when you type it, you don't think it's going to do. And so that's why you can have bad things happening. And we'll start with something really bad. Our first 0 day, December 2021. I was not there at that time. But what's interesting, because we're all about transparency, I could find all that information on public blog posts and public repos. And somehow it was useful for me for the interview process, because somehow they were asking for that. So what happened? December the 2nd, a researcher finds a past traversal. Okay. But he's super excited about it. He reported to us, like responsible disclosure and all that. That's fine, like GPG encoded and all that. So all the clean thing. And then just after that, he said, wow, I found a past traversal. And you can see like all those links, the links work. So you take the slides and you will see all the comments, all the tweets, all the details, all our comments on PR and all that. So he tweeted about it. And of course, what happened a few days after? Well, you tell people, hey, there's gold here. And people try to look at it. And after a few days, we saw that our hosted instances, people were actively using the past traversal. So just because someone said there was a past traversal, several other researchers found it, and they didn't tell us, and they tried to exploit it. So it was clearly a 0 day. And we released the fix on December the 7th. So basically, we were working on it. And then when we saw that it was actively exploited, all the companies stopped working and just like focused on getting it shipped. And then the question was, when we did the post-incident review, like, what the hell? How could it happen? Like, we are using like standard Go libraries. How can we have past traversal stuff for things where the language says that it's secure and it's simple? Well, here is the culprit. You will see why. So, filepath.Clean. Like, just reading the name like that, it sounds like if you're lazy and you just look at the name of the method, you say, yeah, it's going to clean everything. If you look at the doc and you just read the first sentence, it tells you like clean returns the shortest path name equivalent to path, which seems to be like exactly what you want. If you want to avoid past traversal, you get your input, you give it to this method, and then the path is clean. Shortest path, no problem. But in fact, it says like purely lexically processing, blah, 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 those 4 rules. I won't tell them. It's super confusing. You read that 3 times, you're still not sure what's happening. And all that. I don't want you to read all that. Again, all the links are working and all that. When it gets like complex like that, I like to play with a few code samples to be sure I understand the doc. Which says a lot, because when the doc is unclear, then it's a really bad source of confusion. So basically, my understanding, when you read that, it says like, it will remove all those dot sequence, which is perfect when you want to get rid of past traversal. And it will do that for all the inner elements. And also for the first element, if it starts with a slash, which means then it does not remove the first dot if it does not start with a slash. So for that, making sure you understand the doc, you go to the Go playground, write this simple like snippet, and then you see that, yeah, in fact, if it starts with a slash, then everything is clean as expected. But if it starts with a slash, then it's not going to be cleaned up as expected. So what we were doing, yeah, well, classic path traversal stuff, I guess. We have a web parameter. We have plugins in Grafana where we need to load extra files. And then what we were doing, we were then just, okay, cleaning these parameters. Say, hey, yeah, we're not stupid, doing some input validation. Let's clean it. And then that should be fine. And then again, you click on the vulnerability link, you see the old commit that had the broken code, because of course today this is fixed. What you can see also, because it's all open source and public repos, you can see also all the comments on the pull requests and all that. And there's something that's interesting, even in the source code. There's a comment that says like, yeah, well, go sec this security linter, it's complaining, but one of our software engineers said, yeah, well, we can ignore this warning because we are cleaning things as we should. So we had a linter that warned us, but we were sure that we were doing the right things and we kept track of it. So at this stage, it looks like, well, you know, everything is under control. You have like some security linters in your CI/CD pipeline. People spend time looking at the results, save like as comments, like why they decide to ignore something and all that. And then what's even more funny, if you look at GoSec and then what's about like these G304 finding, it says, yeah, well, you know, you're giving something as file path. Yeah. And then there's a link in this GoSec warning that's called the right way. And then what the right way is telling you to do? Well, use filepath.Clean and then you're safe. So we are like using code, the linter complains, but we are using filepath.Clean, and the doc of the linter says you should use filepath.Clean. So like someone reviewed the PR, reviewed this comment, and then say, yeah, well, anyhow, GoSec tell me like this is the way, so we should be fine. We were not. So what we did, again, you click on this link and you see the fix. We just append a slash, and it seems to be fine. We saw that before, like if the first element starts with a slash, it seems to be okay. We added some unit tests, and then we created like a few follow-up issues in our post-incident review process, like to have, let's say, more control about this kind of like silence rules and all that. Okay, that's fine. So that's the fix that went out on December the 7th, 2021, and then fixing the 0 day and all that. But everyone was still like troubled. Let's say like, is it enough? It kind of looks of a hack. Like we need to put a slash in front of it. Why Go is not doing it? And then like maybe bad things can happen like with Unicode characters or whatever. Like, are we doing the right thing? Because it's already exploited. People know we have a path traversal. Now there's a fix like that. So it's going to be super easy, for other people to try to say, hey, okay, now I'll try other path injection, and it's likely to succeed because when you look at the fix, it doesn't seem that strong. So here comes Go Fuzzing. So the goal of fuzzing in general, and then in Go, you see the context, it's a bit different, but basically it's you write predicates and you expect to write those predicates saying like those things should never happen. And you want to throw an engine that will try to find counter examples that will break those predicates. So it's kind of the opposite of security requirements, where security requirements are telling you like, yeah, you should do that. Well, whereas like here we are writing things that this should never happen, and that's it. And then what will the fuzzing engine do? It will generate many pseudo-random input and see if the predicates are broken or not. And if it finds a predicate, it stops and it says, hey, your code is broken, security-wise, this bad thing can happen. So what's cool is Go included natively fuzzing from version 1.18, which is about like 1 year ago. And the way they did it is super neat from a developer perspective because it's on top of unit test. So it's almost unit test. By default, they behave as unit test, and then you activate the fuzzing flag, and then they start to do all the magic of a never-ending loop, multi-threaded, so that they can test like a lot of findings and all that. Meaning that you can have your unit test, you just need to like write them a little differently. They run in your pipeline as usual, and then at some point you want to gain confidence that your helper works okay, and then you say, okay, now I'm going to spend like 10 minutes fuzzing. I switch a flag, I run it, and then I see if it finds something or not. There's a tutorial which is not that crystal clear, so let's just use this vulnerability as an example. To make things easy, I extracted all the code, just put our clean path method here, where we do this hack of putting a slash in front of it. Again, if you're interested to play with it later on, I created a public repo. You download the source code, you play with it, and you tell me when it gets broken because of whatever new Go version. Things can happen. The fuzzing test, we don't care about the syntax here and all that. What's interesting is you see test cases. Basically, you give, let's say, input as starting points, like things that should look okay and things that shouldn't really look okay. And then from there, fuzzing will start doing minor mutations and move things around and all that, and up until it finds something. And what's important are the predicates. So here we are saying that once cleaned, all the inputs should start with a slash. If it's not the case, an input has been found that is breaking the assumption. And we try also to say that, well, if we see a slash dot slash in the middle of a clean input, like our input validation is just bad. It's not working. And we have found like an input that's breaking the rules, and we want to be aware of it. To launch it, super easy. You just need the correct Go version. And to activate the fuzzing loop, you just put like -fuzz equals fuzz, and then it starts throwing things at you. Yeah. When you do so, you'll see that in fact you're wrong when you're writing the predicates. And that's really interesting, which means like sometimes it's harder to test your validation logic than to write the validation logic, which means that most of the time your validation logic is incomplete because you didn't think about everything. So it's trial and error. You say, hey, here are my predicates. You launch them. 2 seconds after violation, you see an input that, wow, this input is like obviously wrong. I need to fix my predicate because most of the time it's a predicate that's wrong. And then sometimes you get stuck. We'll see an example just afterward. You don't know if it's like, if the input is legit or not, should you process it, and is the output like something you should expect or not. So for example, if we use this example, and then we use a predicate which is like, I don't want a dot slash in my clean string, then after 0.00 seconds, so like almost right away, Go says, hey, I found something. Like if you give it like 0.0, then you end up as a result which is like /0.0/0. Like, is it a legit input? Is it a valid output? It's like, it's super hard to know. So that's where like fuzzing has proven like super useful, so that you challenge yourself and say like which kind of input you should accept. And so before path traversal, what we want to do is making sure that the input, like really, does it ever make sense to have this kind of path 0.0 and all that? So it helps us fine tune like our validation logic and all that with all those corner cases. And when we saw there was value, we use it for like a bit more complex things where we didn't have 0 days. we say like maybe it's a good idea to try to be a bit proactive. Again, we are using filepath.Clean at other parts of our source code, and especially we have plugins and we sign those plugins to make sure they have not been tampered with and all that. And for us, when we do this signature, it's super important that all the file paths in the plugin match what's in the manifest. So we are using filepath.Clean, and then we have like a bit different logic and all that. Again, here you can click on the link, you get the example. I just copy paste the code here to make it like easier to read. We write a fuzzing test for it, and there it gets harder to write. You soon see that when you try to write predicates, if the logic starts to be a bit more complex, it's hard to write it in a clean manner and all that. That's what we try to achieve there. We try to wrap that in method and all that. So it can start to be, like, to be honest, it can start to be hard, and it's not like it's going to work in 10 minutes and then you feel safe. It requires like engineering bandwidth and all that to play with it. So you have to like work on method, trying to see what it does, and then you start getting stuck because you say, okay, this is a Go native library, but I'm not sure if it's really secure now because I don't trust their docs anymore. So somehow you have to re-implement like all those small things yourself so that you compare the Go implementation with what's your definition of what this code should do. So it takes quite a lot of time. But yet it's still useful because you find things. So for example, we saw that we had something broken in our signature plugin if you put like // So basically you could inject kind of an empty file in the signature, which was not a big deal, but yet it proved that our validation logic was broken. And we were expecting people to look at each and every filepath.Clean we had in our source code because it has proven of value. So we fixed it. Click on the PR, you see it and all that. So Go Fuzzing was super useful for that. Barbarous terms now. This is going to be getting hard. Again, you have the links and all that. But before diving in, well, it's a CV, it's public. If you click on it, there's the advisory. And to be honest, when you read the advisory, you don't really understand what's happening behind the hood. Like the advisory says, yeah, there's a rest condition which can lead to privilege escalation. Like you understand it's bad because this vulnerability is a critical, it's a 9.8, but you don't know how it can happen. And then you'll see how the code has been fixed. Like even if you look at the fixed code, you don't really see the link between the description of the advisory and like what's happening behind the hood. It's because, yeah, even though we are an open source company, we still have private customers and they want the advisories to be as generic as possible. That's life. What's more interesting there is how did we learn about it? So this time it's not someone tweeting about it. We were lucky. Well, in fact, it was unhappy customers, like in our cloud versions. They're starting like sending us like contacting support and say ticket and say, hey, I don't understand. Like sometimes like some data on my graph is not appearing. And then when I see the log file, I see like access denied, 403s, 401 errors. This is strange. We had nothing like that 1 week, 2 weeks ago. Like it starts to appear like, well, that's strange. So engineering team like work on it, try to understand, took them a lot of time and all that. And then a really good developer from us like found it, said, hey, yeah, it's a concurrency issues. I tell you the first sentence. I read about it. We have found a shared slice write rest condition when initializing handlers for the middlewares. Good night. It's kind of, we try to decipher that and all that. But what's interesting there is, well, that was a concurrency issue, but it's about something like it's middleware. But what are middlewares? We'll see that they are related to authentication. And then what's really nice here, like with the culture we have, is a developer finds something, a REST condition, you see that it triggers like bugs regarding access denied and all that, and then he pings us, the security team, saying that, hey, yeah, maybe you should have a look at it. Maybe there is a security impact, because the bug we're seeing is customers are complaining that they don't see their data, but maybe some customers are seeing data they are not supposed to see. And no one will ever report you something about that, except if it's really like obvious that you shouldn't see it. So let's see what can we do with that. Before that, a bit of vocabulary and all that we use internally. API routes, middleware. An API route is just basically the mapping between the URL, the public API, like URL you can contact it, and then the business logic that it's calling. And then the middleware is shared code that can either be called before or after the business logic. So basically, instead of copy pasting each time all the same kind of authorization checks and all that, when you call a method, you put it in common components and then you make sure they are applied systematically. And for example, we have middlewares for making sure the user is logged in, which is kind of useful. We also have that's before the business logic, and then after the business logic, we have some middlewares that make sure to filter out the resulting data to make sure you only see what you're supposed to see. So you have two examples below of our source code, where one is middleware and say, hey, you should be signed in, and then you have something strange about snapshots here, where it says like it's public mode or sign in, which kind of the first time you read it is kind of worrying because it's a, hey, well, it's something that either you are logged in or you're not logged in. We'll see that it was a poor design choice. Getting to the hard part here, why appending to slice is dangerous. First, there is a really great article, and not just because of this picture, but it really explains like about like one big page, like why slices in Go are not arrays. Slices basically seems like, if you have to say it in a few words, it's like you have an array of data and you say like, I want this part, this subpart of the array. Like I want starting from 3 to 5, just give me this sub-array. And as a developer, if you don't know Go enough and all that, it seems like, yeah, well, you have an array, it gives me a new array, which is just the only part that's interesting. And then it's well phrased in the article that says there's a common misconception about how slices work in Go that leads to unexpected program behavior. So that's the confusion we were talking about at the beginning and all that, which is surprising to many developers. So that's it. So it's unexpected, not because it's not deterministic. It's unexpected because as a user of the language, you don't think it should do that in that case. And then look, all of that, he said, it's because slices are references, pointers, basically. All of Go, almost everything is copied by value, so that you don't get all this kind of dangerous pointer stuff you can have in C and all that, except for slices, because they're doing that for performance reasons and all that. So again, if you want the full details, the article is really nice, but as a TLDR, well, a slice, in fact, when you ask for a slice, a new object is not created most of the time. The slice is using the real array behind, and only when the array behind does not have, let's say, the correct size. So, and you don't really know, because it's like compiler stuff and all that, it decides to clone your slice. So, which means that sometimes your slice, which is a reference, gets cloned automatically, which means like it is passed as a value by chance. And sometimes it's still a reference and it's as dangerous as a pointer in C. So, the vulnerable code. Oh, well, we don't know if it's vulnerable yet. Like, we know it was broken, there was a bug, and a fix. Again, full transparency, you have access to the pull request where it was introduced. I don't want to show you 15 pages of code that was in this pull request. If you're brave, you click on the link. But I just show you what's important in the pull request, the summary of what is each change doing. It says, well, we are changing the middleware execution model from web handlers to in a slice to web.middleware. Okay, we are changing something about the middleware, and there's a slice in the loop. And then the comment is interesting. It's like, why the hell should we change that? Like, we have many more features to work on and all that. Well, in fact, there were like a few improvements and all that. A bit explained there. Middlewares are temporarily kept in a slice to preserve ordering. Blah, blah, blah. Because before that, when you had 2, 3, 4 middlewares, you did not have the guarantee that they were applied in the correct order, which can be kind of confusing because you say, hey, I want to be logged in, then I want to have permission A, and then I want to filter data like that. If you don't do it in the correct order, you start getting error messages that say, well, sorry, but I can't tell you if you have permission A because I don't know who you are yet because the login middleware hasn't kicked in yet and all that. Okay, so something that made sense. That's hard when you read it and all that. A change that has to be done. A change that was done on authentication logic. So something super, super sensitive. But the pull request was approved. All the comments were fine. And then when you look at the source code, and to be honest, even if I had reviewed the source code, for me, it would have looked nice. It looks clean. It makes sense. We need this change. And then when you read it, you don't spot anything. And of course, we were talking about CodeQL before, we can talk about SameGrep or any SaaS engine. There is no way this kind of thing, will point it out. It's just business logic. But it's business logic about authentication stuff. Now the bug fix, which you can see there, the comment is more useful. Let's say, hey, well, we have to explicitly copy the middleware chain to avoid passing a shared slice to the context. So now, well, we don't say in comment that we had a vulnerability, but yeah, if you just look at the CVE date, the date of this PR, you already find it within 5 minutes, you know it's this code, it's this change. And basically what we are doing, well, we are just enforcing the copy so that we are making sure that we are not using slices as reference from time to time. We just make sure to copy them explicitly and then it should be fine. Should it be? Is it enough? Well, this bug fix was tested in production. We don't see any more errors about access denied and all that. But you never know, especially when it's a rest condition. Maybe you fixed 99% of it. And in 1 week, someone sees it. But then now, with that, we've leaked openly that we had something broken in this authentication middleware. And we know that people are already following Grafana. And they are actively looking on us. Yeah, just to figure we have more than 1 million instances deployed in the wild. That's quite a big number. So that's why I was happy to have been contacted and say, okay, now we've made this fix. Was the code exploitable before this fix? And if it was exploitable, is this fix enough? What can we do about it? And especially, how can we decide quickly? How do you do that in a few hours? So that basically you tell all the incident response team and all that, yeah, well, if it's exploitable, maybe you have to look at your log file for the last 2 weeks and see if any, let's say, ill-intended person has tried to exploit that. So, on this slide, I like to take a step back. And what I do, it's full remote company, so we work from home and all that, but I just go away from the computer and I try to take 15 minutes off and try to just focus on the problem and not on all the mess and that it trigger. So the root cause is, well, because of the way slices are working, sometimes they can be shared instead of being a copy. And then it depends on the sizes of those slices and all that. So it's kind of meaning that, okay, if we want to exploit it, we must force those slices to be shared. And we know it's possible for them to be shared because we had this bug. So it happened in real life. So it shouldn't be that hard to reproduce. So in practice, it means like if we want to exploit it, what we will be trying to do is, okay, so well, let's say we have request A. Is there a way so that request A will receive the middleware lists of request B if both requests happen about at the same time? Can I get to execute like something for user A, but with the checks of user B? So when you do that, of course, you never know if you get a yes or no or I don't know. And maybe you could spend years on that and never being able to prove it. So trying to optimize the chance, or let's say minimizes chances of failure, let's be honest. So first point is, because it's going to be rest condition and it's never going to be deterministic and all that, first decision was to test it locally so that you like avoid all this network latency and all that could make it harder to exploit. And then the decision to make things easier, and because there's like this size parameter and all that, was to focus on endpoints with only one middleware, so that if you make the switch, you are switching from A to B, and you don't have like A, B, C, and D, E, F, and all that, and you don't know what's happening, and all that. And of course, if it's a vulnerability, you want to maximize impact. And so for that, as something when you know the application, there's something which is unconventional. Let's use this word, where there's an API endpoint. If you have server admin access, you can reset the password of anyone without knowing their password. So normally only the super admin can call it, but it's kind of our highest asset there. And we also have a few unauthenticated endpoints. There is a public dashboard feature where anyone can see dashboard of public data, which means that if we can do that, if we can have the reset admin password endpoint called with a public middleware, it means like someone not logged in may be able to change the super admin password, for example, which will lead to this nice 9.8 score. So now, how do you do that in practice? Like, you can try to maybe like write Python script, launch burp, whatever, and then cross your fingers. Or I was lucky. There's a tool called K6. So it's an open source tool that's now part of the Grafana Labs umbrella. Its goal is to provide the best developer experience for load testing. So basically, load testing made easy. Basically, you don't need to spin up 17 Dockers, read 45 pages of docs, resolve 15 broken dependencies, and then you launch something and then you get network errors because like queuing to optimize and all that. So it was kind of a no-brainer for me to try like and say, okay, now let's try to reproduce it with K6. Are really great docs. First time I use it, it was on my to-do list. I say, I need to have a look at it. We wanted to dog food it for security use cases and all that. But then like, well, there's never a best case that under pressure to test if the tool is good. And if the results are good, it's like the tool is really good. And and what's nice is, load testing tool had really bad experience with previous ones. Now it's an internal team, it's teammates. And because it's kind of a highly visible incident, if we need help, like they will help. So that was kind of nice, but I didn't even need help. So there's a demo here. And if you don't see the details, it's going to be shared. This one is super sensitive. I'm sure there are still hundreds, thousands of instances that are running this broken version. They shouldn't be. Please don't play with it against instances that are not yours. So what we will try to do with K6, what's really nice, it's they have a simple JavaScript, let's say, library to express what you want to do. So what we are going to do, we have this admin reset password endpoint, we have a public dashboard endpoint. We prepare a payload where we set the password to dummy password. Here we define scenario. That's what really nice with K6. You say, okay, now I want to have the first scenario. I call it protected. And I'm going to run 60 views. Views, in fact, are virtual users. So basically, it's going to start 60 threads calling that. So there will be 60 virtual users trying to call the reset password endpoint, and there will be also at the same time 60 virtual users trying to call the public endpoint. So quite heavy load there, and we say, okay, we test that for 2 minutes, and we see what happens. So that's the description of the scenario, and then you define, again, predicates, where you say things that shouldn't happen. So you say for the reset password, you try to reset the password, and because you try to call the reset password without any credentials, you say, hey, this shouldn't work because I'm not authenticated. I'm not supposed to be able to change the password of anyone. So you expect the status to be not 200. And if it's 200, you say, okay, stop. Password has been updated. That's really bad. So that's for the predicate for the protected route. And then for the public endpoint, you just say, well, it should return 200. And if it doesn't, like something strange is happening also, there's no reason for it to fail. And so now let's do something crazy. Let's try it. You should never try to demo something that's random, but yeah, Friday night and all that. Let's give it a try. So what you do, you need to run a Docker version. I'll try to zoom in. Yeah. Well, there's nothing magic. Anyhow, you run the Docker image of a vulnerable version, and then the only thing you have to do, K6 run the name of the JavaScript we've seen, starts running, boom. Lucky. Normally it's 5 seconds. It was quicker. So, like, yeah, after a few dozen calls, you have statistics everywhere. It changed the password to dummy password. Let's try it. I'm in. So, which things like, so what we did, so then of course, we tested for a few hours with the same script, the patch version, to make sure it doesn't happen, or at least that it's hard to reproduce. So it's kind of easy to reproduce locally. When you have network and all that, it's much harder to try to reproduce it and all that. But that's enough to prove that, yeah, it's a vulnerability, and then it's a 9.8, the biggest vuln we ever had at the company. And it's something no security researcher found, no one from the security found. It's developers because they had to work on a bug because of access issues at customers' deployment that we figured it out. So maybe there are other rest conditions. And it's something that if people tell you like Go Rust is hard and all that, Rust has much better guarantees against rest condition, whereas Go is, well, as long as you copy things, it's okay. But if you start sharing things by reference, you get things wrong. We also had other rest conditions with maps in Go, because maps are also passed as references because they are too big. So things can happen, but they didn't have any security impact as far as we understood. But maybe we didn't understand well. So we just launched a bug bounty program. We handle it ourselves. Official announcement has not been done yet, so feel free to have a look at it first before there are too many people. We're interested about this kind of finding, the big one. So something like that is clearly worth 20,000. So we've tried to, as Christian said yesterday, to better align the incentive so that in the policy of this bug bounty program, we are optimizing for good quality of reports and all that. So we will pay bonus points for reports that are really well written, where there is a clear POC and all that. We are not interested by automating findings, which is just like copy pasting of noise and all that. So what we learned? Well, filepath.Clean is like super tricky, and you can think that you're protected from path traversal in Go, but you're not. But Go Fuzzing can help you quickly spot that. And then you can include that as nice regression tests in your pipeline if they are not too complex. And then you also learn that slices are a dangerous beast in Go, especially if you start implementing like authentication logic yourself in multi-threaded context and all that. And we've seen that, well, if you need to exploit rest condition, like even in different contexts and all that, like have a look at K6. It can help you like be super productive in validating that. And then I'm happy to take questions.
Well, first of all, thanks for your talk. And my question is, do you think Go should update the method, the one from the first vulnerability, to make it not possible to reproduce what happened to you?
I would say so, but if they've done it this way, they have a good reason to do so and why the algorithm is there. And it's kind of, but they know they got it wrong because they have a go-sec rule, which is that, hey, it's not that good. So, but then now I think it's too late for them to change. So basically they should need to have something which is like filepath.Clean safely or something like that. And then they can have this go-sec rule that say, hey, you should rather use clean safely. And if it breaks things, yeah, just use a dangerous version and beware.
Thank you.
Thank you for interesting presentation. I thought I said yesterday that, of course, Grafana dashboards are a lot more informative than Kibana dashboards.
Yeah, that's why we fork Kibana, of course.
Yeah.
We change the colors, so and we don't like pie charts.
Well said, well said. But jokes aside, I'm not a developer. What I didn't get in your presentation, and please explain it like I'm 5, is you have a race condition in your code. You fix the race condition. Why would you need to run performance tests, whatever you did? Can't you prove that the race condition is gone, or couldn't you change the architecture so it's really gone? Because for me, it feels like you don't really trust your fix.
Yeah, and that's true. And that's true. And it's like basically with multi-threading, it's hard to prove. And if you want to prove it, use Rust, basically. And that's the only solution, like for me. Otherwise, it's really super hard. Either you need super, like, limited programming languages that are only focusing on multi-threading, and they are, like, let's say, rest condition proof by design, but they are super hard to use, super hard, which means you're not productive, which means you will not be able to deliver enough features, and all that. I would like to be totally honest. I think the original sin here is we have too many custom authentication logic. And maybe we shouldn't play with that. We've played with dangerous things and we were not mastering them enough.
So that's the cost of doing multi-threading.
Yeah.
Okay, thank you.
And that's the cost of doing multi-threading without realizing you're doing multi-threading.
Okay.
Yeah.
Hi, thank you for the talk. Go, the framework itself has a data race detector that you can have enabled with go test minus race, but you recommended another one, so I would like to know how it compares and if you prefer the other one because go data race detector was insufficient.
I couldn't hear you well, sorry.
Sorry. So the Go binary itself has a data race detector.
Yeah, it cannot spot it.
Okay, thank you.
I mean, we tried. Yeah. But it's like, it can find obvious things, which is good because it catches, like, if you start doing multi-threading things and then you say, yeah, I don't get it. I don't even understand the error message. We say, like, I shouldn't play with it. But this kind of thing is much more subtle that it cannot find it. Like, basically, it runs forever and you don't get any results from it.
Well, thank you for your presentation. Thank you for the talk.